All right, everybody, welcome back for the second day of logarithms. Today we're going to discuss the properties of logs. So let's get right into it here, okay? A lot of times people associate the properties of logs, they compare them to the laws of exponents because you're kind of doing the same thing. The product property here, okay, when we see multiplication, we can add, okay, these numbers here. So when we have the log of m times n, we're doing log base b of m plus log base b of n. Okay, another example of that, if I have log, I'm just going to make up a base, log base 2 of 12, okay, that would be the same as log base 2 of 1 plus log base 2 of 12, right, because 1 times 12 equals 12, right. You could also say this, because 6 times 2 is 12. And you guessed it, 3 times 4 is 12. Okay, so all of those are equivalent to log base 2 of 12. All right. A lot of times you're going to see not only just with numbers, but you're going to see numbers in variables or expressions in there. Okay, so kind of like the example, we have 9x, so we break it apart with 9 and x. So however you can break it apart with the factors to yield the product there, you are able to do that. All right, quotient, you're subtracting. Okay, just like the quotient rule of exponents, you subtract the exponents. Now we subtract our numerator and our denominator. All right, so an example here, if you have the log base 1/4, again, the base could be anything, of 4/5, all right, log of base 1/4 of 4 minus log base 1/4 of 5. All right, you could do that with any division problem or expression as well. Okay, the power rule here, the power property is very important as well. We can see that what changes, log base b of m, log base b of m, all that's the same. Okay, the only thing that changes here, okay, is this exponent. All right, so we can see that the exponent here comes down and becomes a coefficient, or if we go the other way, the coefficient would come up to be the exponent. All right, so we can see that x came down, became the coefficient, or we moved it back up and it became the exponent. Okay, that one's very important as well. We'll see that one today. Okay, and the last one is the equality property. You know, a lot of people connect this with, oh, we can solve for variables in the exponent. If we get the bases equal, then we set the exponents equal. Okay, if the bases are equivalent, then the exponents are forced to be equivalent. Same idea here. All right, if we're looking at log base b, okay, and log base b, if that's the same, you're looking at the same base, then you just set the remaining equal. Okay, in the example, it's pretty evident. Log base 8 of that equals log base 8 of that. Well, if we throw the log base 8 away, you just set equal 3x minus 4 to 5x plus 2 and solve. Okay, so we'll see some examples of this, but the important thing here, the important takeaway is, you know, when you see addition, okay, that means multiplication. When you see subtraction, that means that goes on the bottom and you're dividing by that specifically. Okay, the exponent becomes the coefficient becomes the exponent. Okay, we go back and forth with that. And then the equality property, if we're looking at two logs with the equal bases, we just drop the logs in the bases and set the remaining expression equal to each other. Okay, so these properties of logs are going to be come in handy when we are expanding and condensing logs. Okay, so if we're expanding logs, okay, you're going to be given it in the form of this right here. Okay, and then you have to expand it and put it in that form. Okay, condensing means you're going to be given the expression addition, subtraction, and then have to condense it into writing log one time. Okay, so again, these properties go back and forth. So expanding, if a value came from the numerator of the log, it's going to remain positive. If the value came from the denominator, it's going to be negative. Okay, so that is the quotient and the product property. The negative right here, that goes in the denominator. Okay, if everything's positive, it stays up in the numerator. Okay, so going the other way with it, Condensing, if the value is positive, it's going to stay in the numerator. If the a value is negative, it will go down to the denominator. Okay, so let's just apply those expanding and condensing rules to a few examples. Okay, so first one here, okay, log 5 plus log 2. Okay, because it's addition, we can multiply this times this. All right, and you're not going to write 5 times 2, you're going to multiply it. So that's going to be log of 10. All right, so what is the base here? Okay, remember, just a reminder, if there's no base noted here, it's always base 10. Okay, you do not have to put that there, but make sure you know it because you will use it in the solving for the next lesson. Okay, log x plus log 2, right? Because it's addition, we're going to multiply. We're going to write the log one time, and x times 2 is 2x. Okay. The next one, we have 3 terms here. We have some positive, we have some negative, we have some with a coefficient. So make sure we apply all the rules that we possibly can. All right. For the third one, okay, I'm going to take this coefficient, bring it up here. Now it's an exponent. Okay, so that 3 is no longer there. All right, so I'm going to write log one time. Okay, because our first term there is positive, x cubed goes in the numerator. Our second term is positive, so the y goes in the numerator. And our third term is negative, right? There's our negative symbol, so that z is going to go into the denominator. Okay, so we have the log of that expression, x cubed y over z. All right, let's try the next one. Same thing, coefficient becomes the exponent. That's no longer there. That's positive. So we have x cubed in the numerator. Okay, our next middle term there, negative log or minus the log of y, because it's negative, that y goes in the denominator, and because the z is negative as well, that goes in the denominator. Okay, so anything negative goes downstairs in the denominator. Positive stays upstairs in the numerator. All right, now let's expand some. Okay, so now we're going the other way. All right, so we have to figure out what operation we have. Is it multiplication? Is it division? Do we have a power? All right, we got to follow the laws. So here I'm multiplying clearly, 2 times x, so I can split that apart with addition and say log of 2 plus the log of x. All right, this next one, I'm going to do it in 2 steps, okay, but the better you get, you might be able to consolidate this. All right, so now I have log base 5, don't forget to carry your base, okay, of x squared plus log base 5 of y. Okay, many of you might think that this one's done. Okay, however, you cannot have this exponent here. All right, we have to take that, put that out front as a coefficient. So it's fully expanded. So we have 2 times the log base 5 of x plus log base 5 of y. And that is your final answer for that guy. Okay. Third one, okay, we have log of x times y and then divided by z cubed. Okay, so we have 3 things. We're going to have 3 terms now. So let's do log of x. Because we're multiplying, we're going to add log of y. And then we're dividing, so we're going to subtract log of z cubed. However, I cannot have this exponent here. That needs to come down and become the coefficient. So the final expanded form is log x plus log y minus 3 log z. Okay. All right, let's try this last one here. 4 terms. Okay. Hopefully you're ahead of me with this and you already have it written on your paper. All right. I'm going to do all this at one shot. Log base 2 of w plus, I know the exponent is going to become the coefficient, so 2 log base 2 of x. Now I focus on my denominator. Again, those exponents become coefficients, but they're going to be negative because they're in the denominator. So 2 log base 2 of y, same thing with the z to the 4th. Exponent becomes a coefficient and it's negative because it's still in the denominator. Log base 2 of z. Alright, so the better you get, you can combine those steps with the power rule exponent to coefficient, coefficient to exponent. All right? Okay. So some of you might be wondering, okay, what's the point of all this? Why do I have to expand, condense, all this stuff? Because logs do evaluate, okay? We can use these properties to rewrite a log expression as a single log so we can evaluate or use the inverse operations to actually solve the logarithm equation or expression, okay? So here's a perfect example of what we mean as we look at this question. Okay, there's a lot going on, but we have to kind of look at each term individually, all right? So I'm going to make this coefficient become the exponent, all right? I'm going to do the same thing for the other one. Okay, now what I'm going to do, okay, is I'm going to focus on this all by itself, okay? So I'm going to take log base 5 of 1 to the 1/2 power, okay, and I'm going to do my log trick to exponential. So just off to the side here, I have log base 5 of 1 to the 1/2 equals what? Okay, we can call it x, so 5 to the x equals that. 5 to the what power equals 1 to the 1/2. Well, 1 to any power is 1, and anything to the 0 power equals 1. Okay, so essentially x has to equal 0 here, because anything to the 0 power equals 1. Okay, so this here, this expression on the left, simplifies to a 0. Okay, the expression on the right, log base 5 of 5 squared, okay, what does that equal? Okay, we can call it x. 5 to the x equals 5 squared. Bases are equal, set the exponents equal. That equals 2. So subtraction symbol comes down, and that condenses to do. So 0 minus 2 is -2. Okay? Questions with that? Okay, you can check this answer on your graphing calculator. I'm going to show you that as well. Okay, it requires you to use this math button and then go down to option A, log base. Okay, and you can type all this in. Okay, let me do the 1/2 first. So 1/2, hit math, option A, log base 5 of 1, okay, minus 2, and then again, go to your log base again, log base 5 of 5, all right, and we do get -2. Okay, are there any questions with that? All right, so we can try another example here. All right, 5 log base 2 of 2 minus log base 2 of 4. If we look at here, we can turn this to our exponent. So we got log base 2 of 2 to the 5th minus log base 2 of 4. All right, so what you could do here, and again, if we use our properties of logs, we're dividing, okay, we could take condense this into one log. We have log of 2 to the 5th divided by 4. Okay, so 2 to the 5th is 32. Okay, so that's 32 over 4. So we have the log of 8. Okay, and I keep forgetting my base. Okay, and then I can expand this out. What does that equal? I don't know. We can call it x. 2 to the what equals 8. Okay, well, that is 2 to the 3rd, therefore x equals 3. Okay. So once again, we could confirm this, that we get a 3. All right. You could say 5 log base 2 of 2 minus, oops, let's type it again, 5 log base 2 of 2 minus log base 2 of 4. I forgot my 5. Let's go back in here and type a 5. There we go. So there's our confirmed 3. Forgot my 5 when I checked it. All right. So some of you might be wondering, okay, why did the first one he evaluated each thing separately and then combined, and the second one he combined everything and then evaluated it once? Okay, does it really matter? Okay, that's my question to you. Would it really matter if I evaluated this, evaluated that, and then solved separately? Well, let's see. Okay, we got log base 2 to the 5th equals what? So 2 to the what equals 2 to the 5th. 2 to the what equals 2 to the 5th. Well, therefore x equals 5, so that turns to a 5. Then you have log base 2 of 4 equals what? So 2 to the what equals 4. It's 2 squared. So x equals 2. So that turns to 2. 5 minus 2 is 3. Okay, could we go back and do the same thing for this one? Okay, I think we could. Okay, 1 to the 1/2 power right here is 1. Okay, so you have log of 1 over, and that's negative, so that's 5 squared, right? Okay, so technically, whoops, our base is 5. So we have 5 to the what power equals 1 over 5 squared. Well, negative exponent makes it go to the bottom, so I'm going to reverse that. Base is equal, set the exponent's equal. Okay, once again, just a different perspective. Okay, so you can completely go all the way with your properties of logs, simplify it once, or simplify each separately. In the end, we still get to negative 2. Okay, and we still get 3 for this one. Okay, so we'll practice a bunch more of these when you come back to class the next day. All right, but those are really good examples of applying the properties of logs to evaluate. Okay, the next thing here is, what if we get to a situation, like this here or like this here, where you can't get the bases equal? Okay, we have to somehow get the bases equal. So we apply what is known as the change of base formula. Okay, so your calculators can only handle logs that are base 10. Okay, the graphing calculators. Now, fortunately, we have the technology here on our iPads with that calculator, that log base whatever. All right, the TI-83 pluses do not have that capability. All right, so in order for us to solve and get everything to the same base, we use the change of base formula. Okay, the change of base formula is written below here, log base b of x. Okay, this is the natural log function. Okay, we're primarily going to use this one. We only use this one when we undo e. Okay, so our continuously compounded interest formula, e to that power, we're using natural log to undo that. Okay, so you're going to take log of that divided by log of your base. So one thing to remember is you always are dividing by log of your base. Okay, so to do this, if we were to do this the old way and do our e trick, 4 to the what power equals 15. Okay, we wouldn't know what to do. If that were 16, I could do it, make it 4 to the x equals 4 squared, but it's 15. All right. I know it's going to be just below 2 because 15 is just below 16. However, what is that answer? All right. The shortcut here is the change of base formula. So you're going to take the log of 15 divided by the log of 4. So let's evaluate that and show you that it's going to be just below. And here we just use the straight log button. Log 15 divided by log of 4. Okay, there's your 1.95. We knew it was going to be just below 2. Okay, the next one, same thing. Log of 4 divided by log of 20. Okay, we get 0.4628 if we're rounding up. Okay. Again, if we rolled the log here, okay, and did our e trick, 20 to what power equals 4, we cannot get those bases equal. Okay, so that's why the change of base formula is there and how it's effective. All right, so same thing this one. Okay, change of base formula, we got log of 3 over log of 7. Okay, we can evaluate that. Log 3 divided by log 7. Helps if you hit divide in the middle. Log 3 divided by log 7. Here we go. If you don't like that, turn into a decimal. 0.5648. And the last one, log of 5 divided by log of pi. So log of 5 divided by log of pi. 1.405. Okay, so you're going to see more of that change of base formula once we get into solving the logarithmic equations for an unknown. Okay, all right, we're going to piggyback on this one, and we talked about the product, the quotient, and the power rule, okay, from our properties of logs. Now we're going to talk about the equality property of logs, okay, and this one's very simple. Okay, we said it before. If we are looking at our log equation, okay, what we're comparing, and if we're comparing the log with the same base, okay, we can drop that and then just set the remaining equation equal, m equals n. Okay, so let's do that here. All right, you might be thinking, well, he just said if it's log same base, well, I don't have that. Well, we can still use our properties to condense this side into one log. All right, so that's going to become the exponent, become x squared. I'm adding, so I can multiply my expressions here. I can multiply the x with the x squared, okay, which gives me x cubed. All right, so a lot of people get stuck here and they're like, what do I do next? Well, we're dealing with log in the same base, log base 10, log base 10, so we can drop the log base 10s and set everything else equal. How do you undo x cubed? Take the cube root. Cube root of 27 is 3, therefore x equals 3. You want to check your answer and make sure you're right. Okay, jam it back in your calculator. All right, type in log of 3 plus 2 log of x. I get that. Is that equivalent to the left side, which is the log of 27? I don't need to put an x in there. Typo. Log 3 plus 2 log x is 3. All right. Now our answers are equivalent. Okay. All right, let's try another one. Look at this one here. Same thing. Let's condense the left side into one log. All right. So we have addition, so we can multiply that times that. Right, so we get log of x squared plus 2x equals log of 8. Once again, I'm dealing with the same log base 10, so I can drop the logs and then solve that. It's a quadratic, so I have to get it equal to 0. All right, and then I can factor it. So x squared plus 2x minus 8, what multiplies to negative 8 and adds to 2? That is a positive 4 and a negative 2. Zero product property gives us negative 4 and positive 2. Okay, so as always, we need to check our solutions. Okay, so if I check x equals negative 4, log negative 4 plus log of negative 4 plus 2, 0 over 0. Okay, well I can't get divide by 0, so this is an error. Okay, why am I getting an error? Okay, so that one doesn't work. Okay, and we're going to talk about that here in a second. Let's check the right side. Plug a 2 back in. Log 2 plus log of 2 plus 2. So that gives me log of 2 plus log of 4 equals 8. Oh, excuse me, log of 8. All right, and if we look at that, okay, log of 2 plus log of 4 equals log of 8. I can use my properties of logs to say, oh, 2 times 4 is log of 8. So that better be equivalent. All right, you can type it in to be sure. and then log of 8, those decimals are equivalent. Okay, so I guess my next question to you all is, why did the 1 not check out? Okay, why is this one not a solution? Okay, I'm going to go down here. It's the same question. All right, I'm just going to use the space provided. Okay, why can't we get that answer? Okay, and the answer is you can't take the log of a negative number. Okay, you cannot take the log of any negative. Why? Why is that true? Okay, so if we just type in here the example we have, log of -4. All right, now the base is 10. Okay, our job is to evaluate that. What is that? So 10 to the what power equals -4. All right, can you raise 10 to any power to get a negative answer? And the answer is no. Okay, if you look at the graph for the log of x, okay, it goes like this. Okay, it's never negative. All right, you can't take a positive base, raise it to a power, and make the answer negative. All right, so that is why you can't take the log of a negative. Okay, because there's no base that you can raise to any power to get a negative output. All right, so no matter what you do, okay, unless you shift this to the left, which our problem is not doing, all right, we will never ever have or be able to take the log of any negative. Okay, so we can discuss that more in class and go over examples of that. Ignore this homework right here. Okay, there's one more question I want you guys to do. I want you to evaluate this. Again, just making this up on the fly. Okay, if we have 3 log base 2 of 4. All right, so there's 2 ways we could do this. Okay, the first way is if you just handle this. Okay, so if you have 3 times whatever we're going to get out here, 2 log base 2 of 4. So this right here, I don't know. So 2 to the what is 4. 2 to the what power is 4, so x equals 2. Okay, so your unknown is 2. So all of this turns into a 2. And then you have 3 times 2, which equals 6. Okay, the other thing you could do, okay, is if you went ahead and used your properties of logs, all right, and said, that becomes, the coefficient becomes the exponent, so this turns into log base 2 of 4 to the third. All right, so what is this equal? Okay, I always put x there, okay, question mark, whatever you want. So 2 to the what power equals 4 to the third. Okay, this looks like a question now that we should have done after lesson 7 too. All right, the second part of that. If the bases are equal, the exponents are equal. So I can get the bases equal. 4 is 2 squared, all to the third. So that gives me 2 times 3, which is to the 6th power. Bases are equal, drop the bases, x equals 6. Okay, so we can get 6 either way. Okay, so we evaluate that, 6 there, 6 there. So once again, we talk about perspectives and different paths we go down. Did we break any rules? No. Okay, we followed the math. We didn't make up our own rules to make it work. Okay, we used the rules of math, we used the properties of logs and our knowledge to make sure everything does work out mathematically and we remain equivalent. Okay, so come back next class and ask any questions you have, and we will be sure to have a variety of examples to go over to give you that foundation, to give you different situations and scenarios that you can be put in and potentially have to expand, condense, or evaluate using and applying the properties of logs.